Determining molecular polarity. So to determine molecular polarity, there are a lot of steps involved, and to illustrate these steps, we're going to use an example compound of CH4. So the first step to determining molecular polarity has to do with the bonds and non-bonding pairs and drawing the Lewis dot structure for the atom. So when drawing the Lewis dot structure for a compound, there are a few rules of which atom goes in the middle. The first rule is whenever carbon appears in a compound, it always goes in the center. Oppositely, the second rule is that if hydrogen appears, it always goes to the outside. So as you can see in our CH4 example, because there is carbon present, I have drawn the carbon atom in the center of the Lewis dot structure. And because there is hydrogen present, I have drawn each of the 4 hydrogens on the outside of the center molecule. So once you have, side note, if there are no hydrogen or carbon present in your compound, then the atom with the highest electronegativity value would then go in the middle. Once you figure out which atom goes in the middle, you would draw the Lewis dots around the structure as you normally would according to the valence electrons. So as you can see, I've drawn carbon's 4 valence electrons represented by blue circles, and then I have drawn each of the hydrogen atoms bonded with the carbon represented by light blue X's. So the next step, step 2, is very related to the first step. Step 2 is shape, and it's related because you need the information from step 1 to do step 2. So to start step number 2, you're going to be looking at your Lewis dot structure, and we're going to look at the number of bonds and non-bonding pairs on the central atom only. So when you do this step, only focus on the atom in the middle, not the ones on the outside. So by bonds, it means if the 2 atoms next to each other are completely satisfied. So as you can see, each of carbon's valence electrons are met with a valence electron from hydrogen, which means this would be a satisfied bond, and so each of these would be a bond. So if you count, you have 1, 2, 3, 4 bonds in this example. And next, you would want to count your non-bonded pairs. But as you can see, because each carbon electron is met with a hydrogen electron, there are no electrons of carbon that are not satisfied, and therefore there are 0 non-bonding pairs. And so the next part of this process is to use these numbers and look at our shape table to determine the actual shape. So this is the table that lists the different shapes there are and the corresponding number of bonds and number of non-bonding pairs that will help you determine the shape. So as you can see, linear would have 2 bonds and 0 non-bonding pairs, or 1 bond and 1 or more non-bonding pairs. A bent shape would have 2 bonds and 1 or 2 non-bonding pairs. A pyramidal shape would have 3 bonds and 1 non-bonding pair. And a tetrahedral shape would have 4 bonds and 0 non-bonding pairs. So based on the numbers we just got from our example of CH4, which were 4 and 0, the compound CH4 would be tetrahedral shaped. The third step of this process, step number 3, is symmetry. So this step is very straightforward. It just includes rules that you have to memorize. There are 2 of them. The first one is if you decide that your compound is symmetrical, that means it is a non-polar compound. The second one is if you decide it is non-symmetrical, that means it is a polar compound. These rules are just ones you're going to have to memorize and just know when it comes to IMF. But to determine symmetry, we're going to be looking at our Lewis dot structure again. And so these yellow lines represent the many ways you can cut this atom in half. And so you'll have to visualize this in your head to decide whether or not it is the same on both sides. So if you take a look at this CH4 example and the yellow lines, as you can see, any way you try to cut this atom in half, it's going to be the same on either side. And if it is the same on either side, that means it is a symmetrical compound and is therefore non-polar. A further side note, if the molecule has a bent or pyramidal shape, it can never be symmetrical. It will never be symmetrical. However, if it is linear or tetrahedral, those shapes are usually symmetrical, but in some cases cannot be. So you just always have to reference back to your Lewis dot structure and visualize these lines to see if it's the same on both sides. So our next step, step number 4 to take this further, is to decide what the strongest IMF is for each compound. And so just like step number 3, these are just rules that you're going to have to memorize and know. So there are 4 of them, and if the atom is non-polar, that means the strongest IMF is going to be London dispersion. If it is a polar compound, that means the strongest IMF is going to be dipole-dipole. Now, if it is polar, but it includes hydrogen bonded with nitrogen, fluorine, or oxygen, it is hydrogen bonding, not dipole-dipole. So hydrogen bonding can still be polar, but if it includes hydrogen and one of these 3 elements, then it's hydrogen bonding instead. And finally, if the compound includes ionic bonds between all atoms, then it is just ionic. The 5th and final step of this process is to rank the boiling points for your compounds. And so to do that, we just use this handy scale. This scale increases from left to right, from low boiling point to high boiling point, and in order from lowest to highest boiling points. The IMFs are rated as number 1 being London dispersion as the lowest, dipole-dipole as the second lowest, hydrogen bonding as the second highest, and ionic having the highest boiling point.